When physically measuring using a measuring instrument, there are several sources of possible error and uncertainty. Okay, we make mistakes. I know that. So let's go over what some of them are. So make that a bit bigger so I can read it. Errors occur if the zero on the scale of the measuring instrument, so your ruler, does not coincide with the end of the object or with the pointer on the measuring instrument. So say you're measuring, you're talking to your buddy, you're not really watching what you're doing, and you don't actually line up the zero correctly with the end of the line or whatever it is you're measuring. So that's when you can get an error, okay? That's usually a human error because you're the one who hasn't measured it up and calibrated it or put it on the object properly. The second error occurs if the end of the measuring instrument has been damaged in some way. So in this case, this person has started from the 1 because the end is damaged and she's lost the 0, or he, and maybe they have measured incorrectly. Okay, so the next error could be a calibration error. So this can occur if the scale is not accurately marked on the measuring instrument. So maybe it's too small, it doesn't have any millimetre little lines if it's a ruler, and it's really hard to figure out anything that's in between 0 and 1 centimetre. So that's called a calibration error. That's when your instrument isn't really well marked out. Another one is called a parallax error. You may have heard of this before in science. That's when you're not looking directly in line with the particular object that you're trying to measure with your measuring instrument. You might be looking down at an angle, or you might be looking at it from the side, and it's actually making your measurement be out by a small amount. And there's always going to be some sort of error due to the limit of reading on the instrument itself. Okay, so if it's not really marked well, that's when you're going to get some sort of error because the instrument is not marked out well. So repeating a measurement a number of times and averaging the values can reduce the effect of any errors. So as a result of the accumulating effect of errors, when calculations are performed with measured values, the following conventions are usually applied. First one, when adding or subtracting measured quantities, the degree of accuracy of the answer, sometimes call this the precision, is limited by the measurement that is accurate to the least number of decimal places. We'll do some questions on that soon. When multiplying or dividing with measured quantities, the degree of accuracy of the answer is limited by the measurement with the least number of significant figures. We'll do those in a minute too. All right, let's see. Turn it back. Let's see if we can do the bottom of this sheet now. Okay, here we go. So here's exercise 2E, error and accuracy in measurement. So question number 1 says, student measured the length of his textbook using a ruler marked in millimetres. The results were 256, 255, 255, 254, 254. You have to average these measurements. Do we remember how to average? You add them up and divide by how many you have. Okay, so you'll notice there I have added 256, 255, 255, 254, 254. Don't forget on your calculator use brackets if you don't press equals at the end of that last 254. And then divide your answer by 5. When I did that, I got 254.8. Now it does say here, need pen miss, to the nearest millimetre, so that's why I've rounded it to 255. So always make sure you read the end of the question so you don't miss anything. All right, let's have a look at question 4. Now I put some thingies over here. Averaging measurements reduces the effects of any errors. Yep, okay, averaging the differences in the measurements could have been caused by any of the errors discussed previously. All right, let's have a look at this one. All right, here's the ruler I was talking about. This one's one of those old rulers that only has markings on the centimetres, nothing in between. Okay, so you have to write down the length of each of the rods. So the rods are the black bit, the ruler is the lighter grey section. So on this one, the rod only comes to just after the 13. So that means that answer is 13 centimetres. Okay, because it's closest to the 13, pretty much. 4B, it's not quite at 14 yet, but it's closer to 14, isn't it, than 13? So your answer there is going to be 14. Question C, again, that one's closer to 14 than it is to 15, so therefore your answer is 14. And in D, that one, the rod is closer to the 15 than it is the 14, so your answer there is 15. All right, so that's just rounding to the nearest number, pretty much. All right, so let's have a go at question 5. The length of a rod is measured using the ruler in question 4. So I'll just put one diagram there so you can see it. And the measurement is recording at 14 centimetres. Would this be the exact length of the rod? Well, we don't really know, do we? So we're going to have to say no, probably not. Because, as you know, up here, we had lots of answers that were 14, but the rods weren't exactly 14, were they? So we're going to have to say no there. Between what values would the actual length lie? Well, what do you think about this one? Okay, could be anywhere, really. All right, so the actual rod, what we normally do is we take half of whatever the smallest unit is on our ruler. So what's our ruler measuring to? To the nearest what? Each of those strokes represents a centimetre, doesn't it? So this ruler is measuring to the nearest centimetre. So to figure out what its precision, if you wish, is we halve that smallest unit. So if the smallest measuring unit is 1 centimetre, we halve that. What's half of 1 centimetre? Half a centimetre. So for this one, we'd say, what values would the actual length lie? Well, it's going to be half a centimetre below the 14 and half a centimetre above the 14. So what's half a centimetre below 14? 13.5. And what's half a centimetre above 14? 14.5. So that's what values the actual length would lie between. All right. Then it says, what's the absolute possible error in stating that the length is 14? Now, I just said we take error as being on either side, half a centimetre. So therefore, our error could be up to half a centimetre on either side of 14. All right, and the last one. How could we find a more accurate value for the length of the rod? What do you reckon? Get a better ruler. Okay, get a better ruler, hopefully with millimetres on it. That would be much better, wouldn't it? Okay, so there's question 5. Now, example 2E2 is very similar to question 6. So I'm actually going to do 6, but I'm just going to follow and see what it says for example 2E2. You can follow that one in your textbook if you like. Well, I'll do it anyway, it's not that hard. So the question says, write a sensible approximation for the example for the result of this calculation, 15.642 plus 8 metres plus 19.21. All right, so the first thing I pretty much do is I'm going to just add all those 3 together. Okay, so I'm going to do that. 15.642 and 8 and 19.21. Remember, line up your dots, or better still, use your calculator, miss. 15.642 plus 8 plus 19.21 gives me 42.852. Now, if you read the think, it says 15.642 is accurate to 3 decimal places. Yep. 8 metres is accurate to the nearest whole number. Yep. 19.21 is accurate to 2 decimal places. Yep, I agree. The least precise measurement is the 8 metres to the nearest whole number. So our answer has to be rounded to the nearest whole number. All right, so what's my answer to the nearest whole number? 43. 42.85 is rounded to 43. Okay, so that's that little bit that was at the end of the very first page in the box at the bottom. So let's do 6 now. It's a little bit more set out. Let's see how we do it. We just need to do it the same, pretty much like what the box said. So 13.65 is accurate to 2 decimal places. 10.9 is accurate to 1 decimal place. And 12.624 to 3 decimal places. So the least precise measurement is 10.9, oh that's a 9, sorry, to 1 decimal place. Okay, so right, I'm going to add those 3 numbers together on my calculator. 13.65 plus 10.9 plus 12.6 7.224 gives me 37.174. Won't fit in there, sorry. Okay, so what's my least precise measurement? This one here. So I have to round 37.174 to 1 decimal place, don't I? How do you do that? Okay, keep the 7, look at the 4, apply the rounding rules to the 4. Your answer is 37.18. Okay, beautiful. Alright, let's try the next bit. See if we can get this done. Number 8 says, same sort of thing, but with significant figures. Complete the following to calculate 7.5 metres. To how many significant figures? Start from this digit. How many digits are there? There are 2. So therefore there are 2 significant figures. Here, how many digits are there? Remember, always start from here. There are 3 digits. So this one is accurate to 3 significant figures. So the least precise measurement is your 7.5 to 2 sig fig. Do that on your calculator. 7.5 times 12.3. That gives me 92.25. Sorry, it's just neater if I make it bigger. Now I have to round this to 2 significant figures. That's 1, 2. So I don't need those 2, but I must look at that one to round it. So that means I'm going to round it to 92. Okay, beautiful. Number 10. 5 students are given the task of each measuring one of the sides of an irregular 5-sided block. Each student measured their own side to a different degree of accuracy. As shown in the figure, write a sensible approximation for the perimeter of the land. Alright, so we're doing perimeter. So first thing I tell you to do, add all the sides. Now I'm going to do that on my calculator. So let's do it. 135.6 plus 87.26 plus 110 plus 94.8 plus 84.467. So when I added them all, I got 512.127, and it's in meters, isn't it? Yep, they're all in meters. Now, which one is to the least number of... Doesn't actually say which one to do, does it? Sig, fig, or the other. So I'm going to take the whole number. Right, we've got 1 decimal place, 2 decimal places, 1 decimal place, 3 decimal places. So to the nearest whole number is the decimal places, smallest one. And then if I look at all of them in terms of significant figures, I've got 4 sig fig, 4 sig fig, 5 sig fig, and then 3 and 3. So either way, 3 significant figures or the nearest whole number is what I should be rounding to. So let's have a look, see if it's different. If I round to the nearest whole number, I get 512. If I round to 3 significant fig, 1, 2, 3, that's actually the nearest whole number as well. So it's going to be 512 meters either way. So there you go. So that's the video for 2E, boys and girls.